Okay. This was the last part I showed, only to compare extremely concise a thread versus a task. Another expression for task is promises in future. It's just another term. Okay. As I mentioned in one of my last sentences, on the left side I have a thread with all issues a thread has, meaning when an exception is thrown in the child dies, the creator dies, the main thread dies, the main program, the process dies. There's no way to overcome this issue, but not with promise in future. When stood async, which is a special kind of promise, throws the exception is transferred to the future, and the future has to handle it. If not, of course, the future dies, but it can handle it. Okay, this is one of the big advantages of promises compared to futures, compared to threads. Okay, there's one issue with threads, which we have. As I mentioned it, or you mentioned it before, when you start in thread, if you say something like stood thread T and you let something run, you have to take care of your child. You have to join your child, or you have to detach yourself from your child. If the thread is still joinable when T, this T here is a local object, when this T goes out of scope, in the destructor of T, stood terminate is called, and you get an ugly error message, which gives you no clue what actually happened. The reason is quite simple. The thread was still joinable while it was gone out of scope. This is such an ugly error message that I want to show it to you. I have a small program which I called thread, and I forgot to join my thread. You see here, I go to Vendbox, I put it inside, and here's my code, just simple. I have a thread T, which displays new thread. Then I ask, hey thread, I ask my thread if it's still joinable, and in this case it says yes to me, but to be honest it says only 1, which means yes. And when I execute this program, you will get an ugly error message. Terminate call without an active exception. The reason is I forgot to join my thread, because when T as a local object goes out of scope exactly here, and the thread is still joinable, such as in this case, stood terminate is called, which gives you this nice exception. How can we overcome this issue? First of all, what's trivial, I can do something like that. Now you see the program behaves as expected. And this one is this one from this T joinable, because this returns a 2, and in this case it's displayed as a 1. So this is quite easy to overcome. But sometimes you forget to join your thread. So how can you overcome this issue? There's quite an easy solution, which is sometimes called scoped thread. And the idea is you take your thread in the constructor and you test in the destructor if it's still, first of all, you test if the thread is joinable. If not, you throw in logical error. And in the destructor, you just join it automatically. Therefore, you cannot forget to join it because you do it explicitly. In this solution is called a scoped thread. Anthony Williams wrote one, or I wrote one. It was quite a common solution to this issue. So you cannot forget it. But if you use C++20, you can just use gthread, which is part of C++20, which is an extended stud thread with the additional capability of joining automatically in the destructor. So therefore, there's no reason to call tjoin explicitly. It's part of C++20, and we will get it. And yeah. Okay. Now I want once more to make a compute-intensive job. What I want to do, I want to build an inner product of two big vectors. Let me show you the original code. Here's the code. What do I have? By the way, with C++14, you know this is quite terrible to read. How many zeros? How big is the number? I don't know. With C++14, you can put in ticks. Now we know 100 million is the number. Okay. So I have a vector with 100 million elements and another vector with also 100 million elements. And I want to just make the inner product out of them. So I take the first element from the first one, the second element from the second one. I multiply it, add it to the second element, multiplied by the second one. That's the inner product. So I did it. To make a little bit fun, I used a random device, I used a Mersenne twister, a random number generator, and I created, you see, 100 million numbers between 0 and 100, uniform distributed. I put it on my vectors by saying push back, and then I calculated the product. I'm not sure if I can execute this on an online PC because it may become a denial of service attack, but we will see. If not, I remove 2 or 3 zeros. Oh, looks bad. Or looks slow, I don't know. Should we use a different one? Okay. Anyway, this is quite a job. And here are the numbers. No, here are no numbers. Wait a second. Okay, I did it. And maybe it's done. It's done. Quite good. It worked. I was not sure if I can get so much memory on an online compiler, but it worked. It depends on the online compiler. Okay, you see, it took nearly 3 seconds. Anyway, this is a job which is quite easily be parallelizable. Why is it so easy to parallelize this job? I have 2 big vectors, and I built the inner product of this one with this one. And of course, I get the final number. Why is this job so easily be parallelizable? How would you parallelize such a job? Calculating the inner product of 2 big vectors. I have, for example, I have 8 cores. Logically, I have 8, physically 4. What I would do, I would take this vector, make it two vectors of a quarter of the size, and just calculate it on one thread, 1/4 of the intermediate sum. Because there's no overlap in data, this is quite easy to do parallel. There's no synchronization issue. Now I show you a few different solutions to this idea. First of all, I do it with a thread. Dot product thread. Here. You see the first quarter of the first vector multiplied with the first quarter of the second vector, and this is the initial value for this sum. And here's the intermediate result. At the end, I just add prod the intermediate result to the final result. And because res is shared, prod is not shared. Prod is a local. Only res is shared. I have to use a lock guard. Sorry, I fixed it. Here's an issue, only for you. What is bad about this example? I fixed it 2 hours before, but you know I have now a PC issue. What is wrong with this? No, the program is right, but it's not as fast as it could have been, could be. What is bad about this solution? Can you go to the mic? I cannot hear you.
You're doing the inner product work inside the lock.
Which is totally nonsense. I only do it once. Just take this, put it here, and it would be fine. Why? You don't have to protect this inner product because it's all done locally. No reason to protect. It's a local calculation. I forgot it, but now you see it. Okay, this is the first solution. It's quite verbose, and here I assumed 4 threads, you see. So I put the work on 4 shoulders. First way to do it. Second way to do it is use std async. It's conceptually similar, but a little bit more concise. I have here std async. Std async triggers, it's a promise, but you can also look at it as an asynchronous function invocation. What does std async do? It produces the result of the calculation of 1/4 of the entire vector. First, second, third, last quarter. I got back and handed to the final result, and at the end, I just added the 4 intermediate results. This is, for me, way nicer to use because there's no need to synchronize anything. Because std async works protected per definition, and the final addition, future.get plus 1, 2, 3, 4, is done in a single thread, so no synchronization issue. This is done with a promise future pair. Conceptually, it's similar to the one before. It's a little bit nicer and similar from the performance perspective. Because all calculation is done thread local. Is this the best solution? Of course not. Do you have another idea? Package task would be a solution, but this is extremely, he said package task. We have in C++ 11 3 different flavors of promise future. One std async, one std package task, and an explicit type which is called std promise. But I will not do it with package task. It's quite ugly from my perspective. There's a nicer solution with C++ 17. Come on. Here, This is the way you should solve it. But nowadays, you are forced to use Microsoft because Microsoft only implemented this stuff. What is called in classical C++ in a product is now called transform reduce. But transform reduce does the same thing, but internally in a different structure. Therefore, it can be parallelized. Have a close look. I say calculate begin end times begin, W begin. This is my initial value, the starting value for the summation. And I say, please do it parallel. That's all. This works since C++ 17. But as I mentioned it, only Windows has implemented maybe 70–80% of this stuff. And now you can expect what you hoped for in my case. I have 8 logical cores. Let's see. I'm not sure. Okay. Now I can hope for, in case I have 8 logical cores, for 8 times performance improvements. I will show you the numbers in a few minutes.
That would use all the available cores. If you wanted to use fewer for some reason, then would you have to use the previous example?
Yes, of course. The point is a different one. This is only, how should I say it? You ask friendly the system, please do it parallel. It's up to the system to decide how to perform it. If your job is extremely small, there will, with high probability, no thread be spawned or started. But if the job is big enough, you can expect something such as a thread. But you cannot specify, do it with 4, 6, or 8. You can assume that here under the hood a thread pool is already running when you just put the task on this thread pool. This is, of course, a quality of the implementation. And yeah, GCC and Clang, with GCC and Clang you cannot do it nowadays, but they will use the TBB, threading building blocks, to make this job done, to implement these 17 features. Okay. Now let's talk a little bit about the future. No, it's not the future. It's C++ 17. Okay. Here only the examples from before. This one we skip. Okay. I have to make, I'm not sure. It's up to you. Now, should we talk now about the future or should we talk about condition variables? What do you prefer? Sorry? Future. Then we come back to the condition variables. Parallel STL. Okay. With C++ 17, you can specify the execution policy. It's not binding, but you can expect that the call is respected by your C++ implementation. You can do it in 3 ways. You can say do it sequentially, do it parallel, or do it parallel and unsequential, which means vectorize. Maybe you know SIMD, SSE. This is this stuff. I will show you a small example on the next slide. Have a look here. I have a vector consisting of 8 elements. I want to add 5 to each element of this vector and store it into res. And what's happening if it would be used, if it would be performed vectorized is special registers are used, which are in my case, 4 times the size. I want to calculate the sum of this range. Of course, I can do it in this way. First plus the second plus the third plus the fourth plus the fifth. What does vectorization mean? I have bigger registers. In this case, this XM1 register has 4 times the size, 128-bit. This means with one operation, 4 elements are added in one step. Single instruction multiple data, SIMD. And have a look at the assembler instruction. In the conservative way, I do it once by one. In this way, I do it with a parallel add, which executes on bigger register, 4 times the size in my case, but there are also other extensions, vectorization extensions, which can go until 512 bits, so quite big. So in this case, you can really expect a 4 times, 8 times, 12 times performance improvement, because there's no reason why not. Okay, this is vectorization. And with this flag here, you trigger vectorized execution. This is the idea. Okay, let's have a look. Here's stud sort. The first version is the classical version. Sort vec begin vec end. Okay, but this part which is written in red are the new overloads, which you can use since C++17. In the first case, it says do it sequentially, it's conceptually the same such as above. Do it parallel or do it parallel and vectorized, the stuff I mentioned a few seconds ago. It's quite comfortable. You just specify a tag and it runs parallel or vectorized. These are all algorithms we get with which will have new overloads in C++17. We have around 100. 69 can now be performed with this execution policy or additional execution policy. And you see a few red ones, they are new. They are new with C++17. For example, maybe you know std accumulate, which is not part here. Std accumulate from C++98, which accumulates its value in such a way that it cannot be parallelized. And this was the reason for getting reduce. Reduce behaves the same, but has the possibility to be parallelized because the structure of making the calculation makes it happen. And here, this is the transform reduce, which corresponds to the inner product I showed before from the interface logic. Okay. Here's transform reduce. Maybe you know from functional programming, there's a function map. What is called map in functional programming is called transform in C++. It's kind of the similar function. And this is a transform reduce in C++. What I wanted to do is, I want to calculate the sum of all this, the sum of the characters of all these words. I have to perform 2 steps. In the first step, I calculate for each string or each word its length. In the second step, I add the lengths together. So at the end, I got the final sum, which in this case 21. I would never do such stuff in parallel, but only for obvious reasons. And you see, I set std execution par, which means it can be done in parallel. I assume nothing would happen here. It would all run sequential because it's not meaningful, because thread creation is too expensive. But anyway. Okay. When you use std sort, or the parallel STL, it's difficult to get a data race, but it's still possible on deadlock. Why is this a data race? What was the reason for numcomp? I want to compare, or I want to sort a few numbers. And I was curious how often my sorting criteria is applied during this comparison. So I created an int which just counts how often it was, how often I used the comparison operator. And of course, numcomp is a shared variable, which is concurrently used. You see, I set std execution par, meaning I have a data race on numcomp. My point is, it's difficult, but you can still achieve it to get a data race with this parallel STL stuff, if you do such crazy stuff. To overcome this data race, it's quite simple. Just make numcomp atomic. Okay, here's the state of the implementation. With Windows, you see, this can all be done in parallel. This function, you can specify do it in parallel, but they actually do it always sequential. Why? They recognized it gives them no performance improvement by doing it parallel. So you can specify do it parallel, nothing would happen. It just runs sequential. And with GCC and Clang, we have a bad state nowadays. They will use the Intel threading building blocks, but this is quite complicated nowadays. Here's a blog post which describes how it can be done with GCC and Clang. I mentioned blog post. My point is, when I published this presentation on CppCon, I also published the source code examples, maybe 15, and you can download it. Okay, and now I think a few performance numbers. Yeah, here. Let me show you the original code. It's called parallel, something like parallel. And then you see what are the performance improvement in my case, having 8 logical cores. Okay. Okay. Once more, I have a vector of, I have 500 millions. Okay, and you know what I want to calculate? I want to apply std transform in a sequential, parallel and vectorized version. This is code for which I show you in a few seconds the numbers. Okay, I have a vector of 500 million elements, and I want to apply std transform to each element. The question is what I want to do. I want to calculate the tangents. What's the pronunciation in English? What's the pronunciation in English? Tangent. I want to calculate it for each element of this vector. You see, I go from the begin until the end, and I apply this operation to each element of this vector, and I store the result in the same vector. I do it sequential, I do it parallel, and I do it parallel and vectorized. I do it by using a lambda function. This is quite convenient. And here's my vector of elements with a lot of random numbers between 0 and a half of p. Okay, what are the performance implications if I do it sequential, parallel, or parallel and vectorized? Here are the performance implications. Have a look. I hope it's big enough for you, or should I make it bigger? This was the sequential, this was the parallel, and this was the vectorized execution. It was what was a little bit astonishing for me, 10 times faster, it should only be 8 times faster, but anyway. But you see, it was 8 times faster at least. Because it was done parallel. I have 8 logical core, which makes a lot of sense in this case. Why is the the vectorized solution not faster than the parallel? Or why is it as fast as the parallel version? So the last version, you see par_ansec, is kind of as fast as the parallel version. Do you know why?
Maybe because you have 256-bit registers, that is 8, where each register can take 8 ints, and that means that each instruction works on 8 numbers at once.
Sorry, I'm totally sorry. Your answer was clever and smart, but this was not the right answer. The answer is quite simple. This is not implemented in Windows. They use just parallel execution. Sorry. It's only a suggestion, you know, these execution policies. But you see, it actually worked in my case, but not for the par_ansec case. Okay, I think now we are done with the future. We should now go back to the past. Yeah. Let me go in a different direction. Challenge. Okay. Okay. Now we have you have often challenge, which means one thread performs something, it wants to notify another thread when it's done with its calculation. So we need a kind of a sender-receiver, producer-consumer scenario. Okay. How can you do that? Of course, we have condition variables. Condition variables are terribly complicated to use in the right or correct way. What can a condition variable do? It can say notify one or notify all, and it can also wait. It can wait without a condition or with a time barrier, such as a relative or an absolute time, meaning such as a time duration or a time point. Okay. This is an extremely easy story in an easy use case. I'm done. I send a signal. Please continue. It should be just as easy as described, but it's not so easy. Condition variables can be how should I say it? Victims to two extremely ugly phenomena. One is called lost wake up, one is called spurious wake up. It sounds crazy, but this is the story. Imagine you lay in bed, you wake up, but it was not the alarm clock. It was the cat which scratched at the door. This is called a spurious wake up. You wake up, but this was not a notification, it was some background noise. This can happen. You have to protect against this phenomena. This is the reason why I have here 3 additional dots, which stands for an additional condition I should use if I want to use condition variables right. Okay, once more. What would you do in your normal life if you will be awoken in the middle of the night and you are not sure if it was the alarm clock or something else? What would you do? You check the clock, and exactly such stuff you should do here. You have to build state. You have to build memory. Okay, the second phenomena I can show you in 5 seconds live. No, wait a second, 5 minutes live. The second phenomenon is called lost wake up. What does it mean? You go to bed, but the alarm clock rang before. You sleep forever. This is a deadlock, you know? This happens. Why? The wait call only recognizes a notification if it's in the wait state. But of course, we have thread, we have no guarantee when which thread runs. This is a deadlock. What would you do in this case? You go to bed and you're not sure how late it is. The same, you look at the watch, you check if it's already 5 o'clock or something like that. Okay. Now I describe you the workflow of condition variables from the perspective of the waiter. Okay. And you have to use them with this kind of pattern or idiom. If not, you are totally open to lost wake up and spurious wake up. Okay, let's start. I'm the waiter. First, I have to grab the mutex, such as here. I put it in a lock guard, unique lock. Okay, I grab it. When I have it, I'm here, and now I first check if return ready is already set. This is my watch, because return ready is set to true before the notification. This means I know it's already too late, I have to stand up, I cannot go to bed. Here, I protect me against a lost wake up, because the notification was before. But we assume ready is false, meaning I go to sleep, go into kernel modus, and I sleep. I release my lock here, because when you did not release your lock, this guy here cannot acquire the lock, which means a deadlock, so you have to release it. This happens here in this workflow. So I fall asleep, then I got a notification. Now two things can happen. First, it could be the cat. When it's the cat, return ready is false, because this event before didn't happen. It was something else, we don't know what. Spurs wake up. I fall once more to sleep, 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 and then I got a new notification. In this case, ready equal to true is set. Now I know, because this is true, the notification must be sent by this call here. Now I know it was the right, correct notification, and I continue until here, and here I release my lock. Okay. I assume this workflow is terrible, but this is the workflow. This is a user interface. This is quite complicated to use. Okay. Let me show you a condition variable in action. Here's a condition variable in action. I have one thread which says waiting for work. This is the waiter, waits for the notification, and another thread which sets set data ready. Okay. Here is set data ready. First, it prepares some work. It locks the mutex. It puts data ready to true, and then it sets, notifies the waiter because it's done with its preparation. Maybe the preparation is this vector, putting something into this vector. This wait call is waiting for this notification using the same mutex here, you see. and waits, but using also this predicate, which returns true when data ready true is set here. This is my alarm clock, this is my state, this is my memory. Then it's quite safe to put my shared work at the index 1 to 2. Why it's safe? Because I know the sender is done with its job. And of course, notify wait is also kind of a synchronization. Okay, when I let this program run, you see it's boring, it's just behave just as expected. Waiting, work done, data prepare, 1, 2, 3. Okay. One remark here. It's not necessary to use here data ready. You can use something else which signals you the notify one was the right notify one or the right notification. I could also use my shared work and check here in data ready if something is inside my shared work. This would also be possible, but I used just a Boolean, only to make my point. And now let me execute it a few times. I'm out of luck. Strange PC here. Yeah, now, you see, now data prepared happens before. In the first case, always waiting was the first guy who was awake. This would be a data race if I wouldn't have used this condition. Why? The notifier says notify one, but the waiter is not in the wait state. This would be alarm clock goes before. I hope I have luck here. Let me try it out. Now I use it without my condition here. Here you see, it's totally fine to use it in this way, but of course now I have a data race. Sorry, deadlock. Let me perform it until I get my deadlock. I will get my deadlock if data prepared happens first. Most of the time, it's a 50-50 chance. Hi, today I'm out of luck. I will get it. Now you see it. Data prepared first, waiting, deadlock. I just forgot to look at the alarm clock. I sleep forever. There are so many ways to produce a deadlock. This is one which is really nice. Okay. How can I kill this process on an online compiler? I don't know. Maybe I should use a different one now. Okay. This is the example I showed you. And now I want to show you something different. How can we overcome this issue? I will present you another solution, which I strongly suggest. Promise future synchronize. You can use promise and future also for synchronization. But promises in future have a lot of advantages beside of condition variables. Why? They have a memory. You have not to protect anything. You have not to use a unique lock or a lock guard. Do you know? Oh, it's still blocked. We will see what will happen in the long run. Do you know why I should here use a unique lock, but I'm fine with a lock guard here? What's the difference between a unique lock and a lock guard? This is a C++ 11 feature. A lock guard can only lock once. A lock guard has no interface. It locks in the constructor and unlocks in the destructor. But a unique lock can call lock, unlock, lock, unlock, lock, unlock. And here I need it quite often. And this is the reason why I used in the waiting step a unique lock, but in the sending step a lock guard, but both synchronize on the same mutex, of course. Okay, let me come back to my preferred solution. Now, once more, back to std promise and std future. Here I have a promise and a future. My promise is called send ready. This is the notification. And it looks strange. In case of a notification, I transfer void. I use get future to draw the future out of my promise. Once more, what is promise future? Two data endpoints connected by a safe channel. One is the producer, one is the consumer. In this case, what happens is notification as a value, sorry. Okay, then my first thread performs the function waiting for work. The second thread performs the function set data ready. Both gets a future and a promise. Why do I need to move my future, my promise? Any idea? Why can I not just copy my future, my promise into this thread? You have to walk.
Maybe then they would not be connected anymore?
No, the answer is different. They cannot be copied. Nearly all entities of the threading facility we have are not copyable. The only exception I have in mind, like this is another exception, is shared future. But all other is not copyable. I have to move it. And here's something totally important. On the application level, when you say std move, it's not about moving, it's just about transferring of ownership. I'm the owner of the future. You thread, I give it to you. You are now the owner. It's called std move, but on the application perspective, if you use it, it's transfer of ownership. I give it to you. You have it, do whatever you want with my future, with my promise. Okay, now let's have a look. What is thread T1 doing? It performs the function waiting for work. It gets the future by R-value reference. And here's the waiting step. That is all. It's just waiting. Imagine what I did before, what I explained about this predicate, about a unique lock, about this workflow. It's all gone. It's just reduced to the essential part, which is waiting. And also here, this one just says set value, which means in this case the same such as notify one regarding the condition variable from before. Please, can you have, he said, can you have timeouts plus, elaborate what you mean.
When you say future wait, can you just have a timeout there?
What do you mean by timeout wait? Ah, okay.
If you don't want to wait forever.
Sorry. We have wait for and wait until. Wait for needs a time duration from the chrono library, wait until a time point. So you can do it, such as, in case of condition variable, such as sleep for, sleep until, you always have these pairs. Sleep, lock, lock for, lock until, always the same pattern. Time point versus time duration. Yeah?
So one thing I never understood with the condition variables, you have the spurious wake-ups. It seems like that problem was solved in the futures. I
Yeah.
always wondered why it was never able to be solved in the condition variables.
I can only cite the origin. The problem is not C++. This is the problem of the implementation of the underlying, which is P threads or Win32 threads or what else.
Well, that's what I was saying. It seems like it was solved in the futures. So what changed between the condition variables and the futures that allowed it to be solved in the futures?
To be honest, I didn't implement in future, but how I would implement is use internally future with a condition.
Okay.
This is easy. But this is the problem is with condition variables. For me, they made the implementation to the interface, to be honest. And they say explicitly, you as a user have to protect against this strange phenomena, which is for me the absolutely wrong interface.
Would you mind explaining when you use condition variables as opposed to promise and futures?
Good point. There's one benefit which condition variables have in contrast to promise future, which I used here for notification. Do you know what's the big difference between condition variables and promise and future pairs? When you go to my class, there's a typical exercise. You should make a ping-pong game. One thread says ping, the another thread waits for the ping and says pong. So ping, pong, ping, pong. You do it by using condition variables. What you can do with promise and future is only say ping. You cannot play a game. Why? They can only be used once. You can send one value, then you have to establish a new promise and future pair. You can send one notification, one exception, only one. You cannot do a ping-pong game. This is the big difference. Not only one, but more synchronizations. You want to make a kind of interplay. This is but if you only want to play a ping game, use promise future pairs. Because look at the structure. There's not much I have to explain, or there's not anything I have to explain here. It's obvious what's happening here. I cannot show you spurious wake up, lost wake up, because they don't exist here. Okay. I think I have one important point to make, and then we are done for today. Okay, this is the last important point I have to make. As I mentioned before, threads have a big issue. When a thread throws an exception, your program is gone. There's no way to overcome this exception, to handle it. You see, this is from the standard. Any return value from the function is ignored. If the function throws an exception, std terminate is called. This function, the function which the thread performs. No way. To overcome this issue, you can use std async, which I already have shown you, and also std promise. So to deal with exception, you have to work with promise future pairs. Here's an example. Wait a second, I show you the entire example, which makes more sense. Here, promise future exception. Okay, let it explain it to me. I create two promises. Both return an int. This is the stuff which goes through the channel. Okay. Then I say get future for creating this data channel between my promise and my future. Nothing is happening so far. I have just two endpoints and connected with a data channel. And the only assumption I make is I produce an int. I produce one and I want to receive one. Okay, now I perform this function diff. Let's see what diff is doing. Diff is a function object which divides A by B. This call sets value puts this value into the shared state. This is the promise part producing something. Because my promise should divide. This is the reason I call it divide. And what can happen when I divide something? I can divide by 0. And this is my exception I want to overcome. So I first check if B is 0. If so, I throw a runtime error. Because this is bad. You cannot divide A by B. This is the good case or good channel if B is not 0. This is the bad channel if an exception is thrown. I handle the exception in the promise. Let's have a look here. I start a thread. The thread performs this promise here. This is the stuff the thread is executing. This function needs some promise and two arguments A and B. Here are they. My promise, 20 and 0, meaning I divide in the first case 20 by 0, which is of course bad. In the second case, I do a good job by dividing 20 by 1. And now I have also to handle this exception in the future, here. The future in this case runs in my main thread, but this is no problem. Okay. Here, when I divide 20 by 0, I get an exception. Therefore, I have to catch it, and I display it here. Here, it's fine, because 20 divided by 1 is, of course, fine. Let me show you the result of this program, and then, if you want, you can ask me a question. I'm still, how long will it take here? You see, you should never use an online compiler for such stuff. Most of the time, here's a compiler out of luck. Fault expression. There's a compiler involved, which I will use now. Have a look. I let it run. Now I can use my own stuff. Okay, the program I showed you before. In the first case, of course, I throw an exception because 20 divided by 0 is not good. In the second case, I'm fine. Now, let me execute it. Now you see, 20 divided by 0, illegal division by 0. This was the error channel. And in the second case, this was the value channel. I produced an exception in the promise, which I can transfer to the future. Both promise and future have to handle the exception. Fine. You see, the program still runs. And in the second case, it was fine, because I divided 20 by 1, which is not an issue. Okay, once more, I'm kind of done. Sorry for this technical issue. I have to say, it was not Windows. It was the VirtualBox update yesterday. I have to fix it. I have no idea. The screen resolution is at least 5 times the size of before. Okay, I will send the presentation. I will send the examples, and you have it to try it out for yourself. And this is all what's left to say for me. If you have not any question so far.
So, first question, why do I have to catch the exception in the promise?
If not, you would get an error because the promise dies, meaning the thread of the thread in which the promise runs dies. With std async, it would not be necessary, but with std promise, you have to do it. Anyway, but in the future, you always have to catch it.
I see. Okay. Second thing, when we go back to the ping pong game.
I cannot go back to
You don't have to go back.
mentally.
Mentally, yes. Is it possible to actually send the another future through the channel and then use it for multiple invocations?
No. You can do what you can do with a package task to invoke it a few times, reset it once more. But with future and promise, there's no way. You have to think in this way. When you create a future and a promise, you create a promise, a shared state, and a future. When the promise puts its value into the shared state, it will be destroyed. There's no way to use it once more. When the future picks up the value from the channel or from the shared state will be destroyed, meaning memory deallocated.
But could you create a new future and then send it to
Yeah,
a shared
but
state?
the point is for each ping pong, you have to always to create a new pair.
Yes.
Which is, what should I say? A lot of work to do.
Okay, and this other thing that you talked about, this is a real channel where you can, like, because many programming languages nowadays also have a concept of a channel where you can actually send multiple items. And
So-
this is
This is just an abstraction, in a mental image for you for this abstraction. Few people call it channel, protected channel, which no one can see what's happening inside. Few one call it also shared state. I call it a data channel, but it's only a picture, mental picture. And the key point is you can put each endpoint to different threads. And that is the nice part. And the channel has a kind of, it's like in rubber. I think rubber is the right word. You can put it in which direction you like. I can put the promise in a thread. I can put the future in a thread. I can let both run in the same thread, whatever I want to do. It's just, they are just connected by future, promise, get, future. This creates the channel.
Thank you.
Sorry.
Yeah, I just wanted a clarification. How will you send the examples in the source code? Is it going to be through email or?
The point is I don't know it. I assume we have a place in which I will upload my PDF, and if I find no possibility to do it, I will attach a few files. But you can also write me an email, so I can send it to you directly if you are extremely curious.
Could you put your email on the screen?
I can put it, but I have a lot of emails. It's quite easy. Just look for Grimm, fairy tales in C++. Wait a second. Wait a second. Here we are. You can use, for example, Schulung modernes CppDE. This is my official one. So, okay. Good. Okay. I think we should stop. Okay.